All right, 10 after 11. Let me make a confession, okay? Teaching in English, damn, is very hard. Okay, if I have the choice, I prefer to teach. I prefer to teach in my mother tongue, which is of course Mandarin. Great, this is very good. 谢谢. But if teaching in English is hard, I would imagine that for you, learning attending a lecture given in English is even harder. Okay, but that is what it is. And I think you choose this English lectures. I trust it's based on your own decision, based on your own will, okay? But nevertheless, learning control is already tough. Learning and control in English for us non-native English speakers, I would imagine is even harder, okay? What I want to say here is that let's just make the best of it. Let's do the best we can. Because I do believe learning in English can give us some edges in the future. First of all, as I said in last week, English is a universal language, all right? So it's a very good way, a very good tool for you to communicate with people don't speak Mandarin, all right? For you to communicate people from all around the world. The other thing is language sometimes is not just a language. Language sometimes reveals different languages represent different cultures, right? When you listen to music written in Mandarin, Chinese, or written in Taiwanese, okay? They are all good music, good sounds, but the sense, the satisfactions, the touch that you can be moved by those sounds are totally different. When I switch to English, it's like my brain is operating in different mode, okay? When I talk to people, when I study papers in English, it's like I am trying to understand another way of thinking, because English to me is more logical, and Mandarin to me, I wouldn't say less logical, but is more emotional, more personal. It's not, at least not more logical, okay? I'm not saying which one is better. I'm saying they have different approaches. And by knowing two different approaches, I think I learn more. I enrich my life more. So learning in English, I understand it is hard, but I also think it will pay off, okay? But nevertheless, one thing is for certain. If I want to get something out of it, I better work hard, okay? I better devote all my effort, okay? Now, there is a very good statement. I don't know who said that, but this statement, I think, deeply blew me. It says, adversity doesn't build character, it reveals it, okay? When I face a setback, when I encounter a failure, how do I react? Do I get upset? Do I get frustrated? Or can I be optimistic and bring out my positive energy and to face the setback, the failure as a man, okay? Not Okay. So adversity review character, same thing. We want to in developing a computer system, we need to understand the system. How do we understand the system? One way to do that is we apply text signals to the system and see how the system respond. And these text signals include state functions, impulse function, as well as you will see, sinusoidal functions. Okay, and when using frequency domain methods, sinusoidal functions are often the first choice. Okay. Now, the other thing you should know that by applying those test signals to the systems, we can define some metrics to characterize the performance of the system. And those metrics can be specified on time domain as well as frequency domain. Okay, if they are time domain measures, then they are defined based on the behavior of the output variables in the time domain. Okay, example include overshoot, rise time, settling time, and steady state error. We will talk about all these terms in the later part of this course. All right. By observing by calculating those measures, they can help us quantify the system responsiveness, stability, as well as accuracy. All right. Now, another thing is that I want you to know is that this course primarily focuses on second order system. Why? Because second order systems are most widely studied in control series. Why is that the case? Because second order systems serve as the foundation for understanding and designing higher order systems. As you will see in the futures, higher order systems are actually made of second order and first order subsystems. All right. Now, second order systems provide a balance between simplicity and practical applicability. Okay, higher order system might be better, but it is simply too complex. First order system is probably simpler than the second order systems, but it is not that useful. All right. So when it comes to practical values, second order systems are way better, way more flexible than first order systems. Now, characteristics often extrapolated and to approximate higher order system behavior. Now, the reason why studying second order systems is helpful is that whatever we do, whatever we learn, whatever conclusion we can draw from studying second order systems, those observations, those results can be generalized to higher order systems. Of course, with some preconditions and with some approximations. But nevertheless, they are a good foundation for studying higher order systems. All right. Now, there is a limitation in this course when it comes to the system that we consider. Now, in this course, we only consider linear system. In a few minutes, I will formally define what is a linear system. In this course, we will only study time-invariant, continuous time, long parameters, as well as single input, single output systems. These are the limitations of this course, which means the systems studied in this course is always linear, time-invariant, continuous time, long parameter, single input, single output systems. All right. Now, let's go to the first limitation. Let's not call it limitation. Okay. Let's call it requirement. Okay. Linear systems. What is the linear system? A linear system is a system satisfies the property of principal of superposition. Okay, what is the principle of superposition? Let's assume I have an input. And in this particular case, let's assume I have a system. And in this particular case, C represents the input and E is the output. Now, let's assume that I apply an input and the resulting output is E1. Next, I apply C2 to the system and the resulting output is E2. Now, the third thing is now the inputs of the system is neither C1 nor C2. It's the sum of C1 and C2. Now, if the system satisfies the property of additivity, then without any calculations, okay, without any experiments, you can directly determine the output of the system. Because here, if it satisfies this property of additivity, then the output must be E1 plus E2, which is the sum of these two outputs, right? Now, next, the property of homogeneity. Let's say the input is C and the resulting output is E. Now, next, the input is no longer C, but C times K, which means C is reduced or magnified by a factor of K. And if the output is guaranteed to be KE, okay, which means if C increases, the output will increase proportionally. If C decreases, and the output will decrease proportionally, then such a system satisfies the property of homogeneity. All right? Okay. Now, what is superposition? Superposition, a system that has the property of superposition will satisfy these two properties simultaneously. And which means if the input is C1 and the output is E1, if the input is C2 and the resulting output E2. Now, let's say the input is the linear combination of these two inputs, right? K1 and K2 are two constants that you can choose. Okay, you can choose whatever values. It really doesn't matter as long as K1 and K2 are real numbers. Okay, that's the only limitation. If that's the case, if the system is a linear system, and that means the system satisfies the property or obeys the principle of superposition, then it goes without saying. You don't have to do any experiment. You do not have to do any calculation or computation. You can directly determine the output to be K1 times E1 plus K2 times E2. All right? Now, if a system obeys this rule, then the system is a linear system. All right? As simple as that. Now, why this property is important? Superposition in control system refers to the principle that for linear system that respond to multiple inputs can be calculated by summing the responses to each individual input. All right, that's exactly what we see, what we saw. Okay, this principle is fundamental and has several important implications. First, linearity. It applies only to the linear systems where the output is proportional to the input. Second, input decomposition. This is the key. Complex input can be broken down into simpler components, analyzed separately, and then combined. Okay, so however complex a signal is, we can take it apart and study each those independent parts independently. And then after studying the impacts of each component, we can finally put them together Why do we want to do that? Because the input, we have very different, many different kinds of inputs. Actually, infinite numbers of inputs. There is no way we can study every possible input. However, if I can find a way to decompose any input into finite number of components, and each of those components can be thoroughly studied by us. And because that system obeys the principle of superpositions, the starting results of, I can collecting the starting results from each components and putting them together and give me the final answer. I can also identify the impacts of each individual components of that complex input and figure it out which part of the input is responsible to the undesirable performance of the output variable. Okay, I can do that. Okay, so I can perform detailed analytical work on my input if the system obeys the principle of superposition. All right. Now, if what I'm dealing with is a linear system, then the total system response is always the sum of two response components. The first is their input response. This response comes from the initial conditions. And the second part of the total response is what we call zero-state response, and it's come from the input, assuming their initial conditions. All right. Why do we have to distinguish these two parts? This comes from initial conditions, which is something we cannot do. Okay. Let me put it this way. Here, there is a car. You want to control the car. What will determine the speed of the car in the future? Two things. After you taking over, how do you drive a car? Decelerate? Accelerate? Okay, it depends your decision, and you now act as a controller. Okay, what you do generates zero-state response. But what will the speed of that car also depends on another factor. What is the speed of the car when you decide to drive that car? What is the initial speed? Okay, is it driving at very high speed, like 200 kilometers per hour? Or it is actually has no speed, right? Now, initial conditions is something already exists. So there is nothing you can do. Okay, you just have to take it, accept it as the way it is. But as a controller, what you can do is manipulate the zero-state response. So by acting zero-state response and zero input response together, hopefully you can achieve a desirable, a more ideal total response. Okay. Now, superposition, the reason why superposition is important, the reason why linear systems are the focus of control system study is because the superposition principle greatly simplifies the analysis and design of linear control systems, allowing engineers to tackle complex problems by breaking it into manageable parts. The key point here is breaking them into manageable parts. Now, how do I take a signal apart? There must be a semantical approach. And we will tell you what that semantical approach is. That is actually the very foundation of frequency domain analysis. With frequency domain methods, we know how to take a signal apart into many components, actually many components with different frequencies. All right, that's the first definition of our system. We want to deal with linear systems. The second is we only deal with time invariant system. What is a time invariant system? Remember, the input and output of a typical dynamic system are function of time. They are time varying. So when we come to the property of time invariant, it by no means the input and output cannot change with time. That is not the case. A time invariant system is a system whose properties do not change over time, whose parameters do not change with time. If the input is time invariant, if the input to a time invariant system such as this is delayed by a certain amount of time, let's say delayed as this, okay, the output will also be delayed by the same amount, but otherwise remain unchanged. If I apply this input to the system, this is the resulting output. If I apply this signal, which is a time delayed version of the original input, if the system is time invariant, then the output will look like this. Apparently, the shape of the two outputs are identical. However, since that the input has been delayed by tau, the output is also delayed by, by t, the output without changing any part of its waveform is also delayed by t. Remember, this is only true if this is a time invariant system. Human body obviously is a time invariant system because our properties, for example, our weight, change all the time. After eating something, after drinking something, my weight is not the same. Same thing happened to our body. You exercise during the morning. You exercise after a meal. The impacts to your body wouldn't be the same. You eat at the regular hour, is the impact of eating in regular hours is not the same as the impact eating it, let's say, right before midnight sleep. Okay, it won't be the same because our human body is not a it's not a time invariant system. It's obviously a time invariant system. Okay, so that's the second requirement. The first requirement, system has to be linear. The second requirement is we only study time invariant system, which means the parameters of the system cannot change with the time. All right. The third requirement is we only deal with dynamic system. This is an instantaneous system. We mentioned that before. Let's focus now on instantaneous. Again, let's talk about more about instantaneous systems. Let me drink some water. I need this. Okay, an instantaneous system responds immediately to inputs with no delay between the input and output. All right, you do something in input, and the outcome will appear instantaneously on the output end of the system. Okay, now how do I have such a? How can I generate such a phenomenon? The key characteristics is including first, zero time delay. The output changes simultaneously with the input. And that greatly simplifies your control problem because whatever you do, the consequence occur instantaneously. All right? That make changing the object very straightforward because all you need to do is to find the right input and the output will come out instantaneously without any waiting, without any time delay. All right? The reason this will happen is because the system is memoryless. What do we mean? What do I mean memoryless? Okay, the output depends only on the current input, not on past input or states. Okay, the output only depends on the current inputs. The past has no impact. That means the system does not have any memory. Okay, does not have any memory. As a result, the past has no bearing with what will happen in the future. All right, that is what we call a memoryless system. Now, mathematically, often an instantaneous system is often described by algebraic equations rather than differential equations. All right. Now, we talked about this before. Okay. When you take a shower, you want to, with hot water, you have to wait a while before the water actually. Now, a dynamic system is certain because the output depends not only on the current input, but only on the past input and its own past states. Okay, so in this sense, it's a system with memory. Okay, what will happen right now on the system depends not only on the current input, but also the past output as well as the past inputs as well as the past values of the output. That is the output history. All right. So the reason why this is happening is because such dynamic systems have energy storage. This system typically store and release energy. Okay. And the impacts of the past output and the past input is actually memorized or accumulated on those energy storage, and we will release when we operate the system, and hence influence the current input. Current output. All right. So, mathematical representation. A dynamic system typically is described or represented by differential or difference equation. Differential equation is for analog model. Difference equation is for discrete time, or what we call digital system. We'll talk about that later. Okay, but for this course, we will only focus ourselves on continuous time system. That is analog systems that can be represented by differential equations. We will not study difference equation unless our time is enough. Now, human body is a dynamic system. Let me give you an example. Food intake is the input. Body weight is the output. Time-dependent behavior. Body weight doesn't change instantaneously with food intake. There's a delay between eating and weight change. That is I think one of the fundamental reasons why weight control is very difficult. Because when I eat a lot, whenever I eat, instantly I become heavier. Then I see the consequence, the negative impacts of overeating. Then it will be easier for me to control my eating behavior. But the negative consequences do not come out instantaneously. It is delayed by some time. Therefore, I ignore the consequence because I don't see it, I don't see it instantaneously. Okay? Energy storage. The body stores excess energy as fat, which affect weight over time. Memory effect. Past food intake influences current weight. A person's weight today depends on their eating habits over previous days and weeks. So human body is apparently a dynamic system. All right? Okay, let's look at a control system. All right? In this course, how do we represent a system? what is the theoretical model of our system? In this course, as I said, we talk about linear time-invariant systems, okay, which can be represented by differential equation. Therefore, in this course, we focus on systems that can be described by such a differential equation. All right? A time-varying control system is a system in which one or more of the parameters of the system may vary as a function of time. When it comes to this differential equation, it means these coefficients, at least one of them is not constant. Okay? If any one of these coefficients is function of time, then this is a time-varying system. By contrast, if all the coefficients, including P0 all the way up to Pn minus 1, including Q0 all the way to Qn minus 1 are constants, then the parameters of the system are all constants. Hence, the system is a time-invariant system. Okay, in this differential equation, the system is represented by the ordinary differential equation itself. And since the highest order of the derivative is n, we call this an nth order system. And the input is r, which occurs on the right-hand side of the equation. Okay, most of the time, we only has one function, r, which is r of p times p0. But generally speaking, this is a general representation, okay? And the solution to this differential equation is the output of the system, all right? So y represent the output, r represent the input. These parameters, these numbers, including a series of p and series of q's, represent the parameters of the system. Okay, there is one rule in defining such a representation. That is, the leading coefficients here is always 1. What happens if it is not 1? Let's say it is 3. Then, if that is the case, we simply divide every term by 3, so that the leading coefficient becomes 1. By dividing everything by 3, the interaction between r and y will not change. All right? So this representation is general. Okay? All right. Now, we talk about linear system. We talk about time-invariant system. And the next limitation in this course is we only talk about continuous systems. Now, the counterpart of continuous time system is discrete time system. And discrete time system has everything to do with analog to digital converter, which is denoted as ADC. In computer control system, real-world signals such as temperature, voltage are often analog, right? Which means their values are real numbers, okay? To use this signal in a digital controller, such as microcontroller or PLC, the signal must be converted into digital through ADC. So ADC is actually, the function of ADC is to actually convert an analog signal to digital signals, all right? ADC work in 2 stages, sampling and quantization, okay? The real reasons we need to use ADC is that to process to set up a real controller, typically we need to use digital hardware, such as microcontroller, PLC, or just personal computer, okay? Those are digital hardware. They can be very powerful, they can be very fast, they can have large amount of memory. but they cannot deal with infinite, infinite numbers of points. Okay, that is the reason why we need to perform sampling and quantization. Okay, now what is sampling? Sampling is the continuous time analog signal is sampled at the discrete time intervals. All right, that is, I have first chose a sampling frequency and accordingly a sampling period, and then discrete time and convert my continuous time signal into a discrete time signal. The second part is quantization. Each sample value is mapped to one or finite number of labels. Now, let's look at them with the assistance of graphs and diagrams. Okay, what is a sampling operation? Let's say this is the waveform of the output of my control system. Okay, in order to process these signals, the first thing I need to do is perform sampling. Typically, the sampling period is fixed. Okay, why do I? And then I will collect these sampling points as the basis of future operations. Why do I need to do that? As I said, no matter how fast your computer is, no matter how much memory your computer has, it cannot deal with infinite amount of numbers. For analog signal or for continuous time signal, it is actually a function of time. And this curve actually have infinite numbers of points. We all know that, right? It actually has infinite numbers of points. So there is no way a digital computer can deal with infinite numbers of points. So we need to make a compromise. And the compromise that we need to make, is that we don't deal with this curve directly. We deal with its equally time-spaced samples. All right? Okay. We deal with its samples. Now, there is one key question, one key parameters we need to specify. That is sampling period. Okay. How dense? What is the density? How dense are my sampling points? Okay. And the answer is short and simple. The faster the faster the waveform, the more sampling numbers you need to have, right? Okay. So I will give you a final answer, based on a mathematical theories. Okay. The answer is that the sampling frequency should be twice as large as the bandwidth of the signal. Okay, that is the final answer. But this answer probably doesn't ring a bell because there are such several terms you don't fully understand. Okay, so the short answer is the sampling period, the sampling frequency depends on the changing speed of the signals. The higher the changing speed of the signal is, the higher the the required sampling frequency is. Okay, there is a proportional relationship. Okay, now the other thing is quantization. Quantization means this is a curve. Now remember, when it comes to a signal, the value of the signal is a real number. So how do you recall a real number? Okay, if you're using digital hardware, you memorize or you recall a real number with finite digits. For example, with 16 digits or 8 digits. All right. Now, a real number can have infinite numbers of information or infinite numbers of digits. Let's say You are dealing with a real number, and that real number is 1/3. And it is 0.0333333 all the way down to infinity. Can you memorize all of them? Of course not. So what we need to do is, after certain digits, we need to truncate them, just get enough. So I can, so what I have done is I sacrifice accuracy for so that my memory requirement, so I don't need that much computer memory, okay, to reduce my computer memory requirement. So a digital signal do that. How do we do that? Let's say it doesn't deal with all the possible values. What it is do is, it's just like sampling. What we do in sampling is that we divide the time into equally spaced points, equally spaced sampling points, right? In quantization, we divide the values of the signal also into equally spaced intervals. Okay, how many intervals? It depends on the number of bits that you assign in memorizing those numbers. Let's say you assign 8 bits, then I can have 2 to the 8, that is 256 labels. If you assign 16 bits, then the number of label is, of course, 2 to the 16th, all right? Which is, I believe, is 65536. Correct me if I'm wrong, okay? And that is quantization. Quantization creates inaccuracy. So quantization error is another uncertainty, another source of inaccuracy in computing. All right? Now, knowing that, based on that, what we just have learned, we can divide systems into continuous-time systems and discrete-time systems. Their differences lie on the nature of the input and output. If the system deals with continuous time signals, then the system is a CT system. Otherwise, if the system, such as a computer or microcontroller, it deals with discrete time signals, then it's a discrete time system. Now, you already understand the difference between continuous time and discrete time, right? A continuous time system is one which signals are defined at every instant of time, all right? A discrete time system, also known as DT system, is one in which signals are defined in specific discrete points in time, and typically equally spaced points. In many cases, a CT system can be approximated by a discrete time system through a process called sampling. We just introduced that, okay? Now, we convert CT system to DT system for computer-based control tasks because why do we want to do that? First, these computers work with discrete data as fixed time interval, okay? Second, they can process CT signals directly. There is no way you can do that because any CT signal consists of infinite numbers of points. Third, computers have limited processing speed and memory. Hence, it cannot deal with infinite amount of numbers. Third, DT systems are easier to implement in software. That's also very, very true. Therefore, it allows for simpler integration with digital sensors and actuators. That is why when put into practice, when we really want to implement a control law, we need to perform ADC, analog to digital conversion, and we need to deal with digital hardware, okay? But that is not what we want to study in this course, okay? But if you learn, if you have a good foundation for CD control, then you can extend your understanding to, you will have a good idea, good understanding about CD controls, then you can extend your knowledge of CD system to DT systems. I wouldn't say without any effort. I would say with little effort, okay? All the theoretical foundations are pretty much the same. All the core ideas are pretty much the same, okay? So don't worry about that, okay? Now, I want to pay more attention about quantization because people often ignore its impacts, especially its negative impacts. Quantization is in the context of computer control system refers to the process of mapping continuous analog values into discrete labels or steps, all right? Now, let me go back one step. Here, there are two things that we need to, two operations. One is sampling, one is quantization. What sampling do is it convert a CT signal into a DT signal. That is what sampling does, okay? Now, this, by contrast, what does quantization does, okay? What quantization does? It converts an analog signal into a digital signal. An analog signal means the value of the signal is a real number. A digital signal means the value of the variable can exist only at a certain numbers of pre-specified levels. Okay, so if you perform sampling on time axis, you convert CT to DT. And if you perform similar sampling operation on the value of the signal, you convert analog signal to digital signal. All right. So DT signal, the definition of DT signal is this. The definition of digital signal is this. One comes from sampling, the other comes from what? Quantization. So DT signal and digital signal are not the same thing. Keep that in mind. But nowadays, when we talk about digital signals, we are talking about DT digital signals because when you need to use the control set digital hardware, you need to perform sampling and quantization at the same time. All right. So nowadays, when we say digital signals, what we really are saying is CT digital signal. All right. Okay. So let's make clarify our understanding on CT, DT, analog, digital. Okay. Now, quantization in the context of computer control system refers to the process of mapping CT analog values into discrete level or steps, making them suitable for processing in digital systems. Okay, that is the reason why we need quantization. Since computers and digital controllers operate using discrete numbers, because when memorizing any numbers, it only uses finite number of bits. That is, only use finite numbers of 0 and 1s, right? Analog signal, that is sample must be converted into finite set of values, which is achieved through quantization. Okay, that is the main nature of quantization. Quantization assigns each sample analog value to a discrete label. The number of this label depends on the bit resolution of the ADC. For instance, APADC has 2 to 8, that is 256 distinct labels. Okay, pick 12-bit ADC provide 4096 distinct labels. So in your computer control system, when using an ADC, probably one of the first things that you need to pay attention to is this. That is bit resolution. The higher the bit resolution, the lower the quantization error. All right, time is up. Okay, I'll see you next week. Thank you very much for your attendance. Okay.